name is Narine Kokhlikyan. I'm a research scientist at Meta. This presentation is about model interpretability with Captum. In this talk, we will cover topics on model interpretability beyond feature attribution and feature importance. In the first part of the talk, we will focus on adversarial attacks and input perturbations. And in the second part of the talk, we'll dive deeper into concept-based model interpretability and recap the talk with future directions. First, let's define what model interpretability is and what it means interpretability beyond feature attribution. As you might remember from our previous talks, model interpretability is an area of AI research that helps us to debug our models and understand how those models arrive to certain decisions. This way, we can gain more transparency about the inner workings of our models and can potentially control their behavior certain ways if necessary. During PyTorch Developer Day 2020, we talked about Captum library and focused on feature attribution methods and their evaluation metrics. We expanded Captum beyond attribution and added support for robustness and concept-based model interpretability, which can be used in conjunction to enable deeper analysis with diverse interpretability tools. This form of new unifies a key area of Captum aside from multimodal and ease-of-use aspects of it. Let's look into adversarial attacks, input perturbations, robustness metrics, and how they can be applied to real models using Captum library. Adversarial attacks help us to fool ML models by adding human imperceptible noise to inputs. In this example, we use FGSM white box attacks to add slight perturbation to the input. The image looks semantically almost the same before and after the perturbation to human eye. However, the model doesn't see that and misclassifies the image as a warthog. In this example, we show how to use FGSM algorithm from Captum library. To use FGSM, we import it from captum.robust package, create an instance of it, and pass our model, which in this case is a ResNet model, and other necessary arguments such as lower and upper bound for input data. We then call perturb on the FGSM instance by passing our input, which is the trained image, and other parameters. This will return us a minimally perturbed input that was misclassified by the ResNet model. We can then visualize this side by side with the original image. As we can see, perturbed image is semantically unchanged, and it will still be seen as a trained to human eye, but the model prediction has drastically changed for perturbed image. The model classifies it now as a plow. Note that we can also use the perturbations not only to generate adversarial examples, but also counterfactuals. In this example, we use minimum param perturbation method to generate counterfactual examples. More specifically, we would like to know how much should we change our input image of a train so that it gets misclassified as suit. Knowing that the index of suit class is 834, we can define such a criteria in an auxiliary function that will be used from the algorithm in order to decide if the model changed prediction label to suit. We can then pass that function to the constructor of min param perturbation along with the model attack function, which performs pixel dropout or ablation in this case and other required arguments. Similar to FGSM, we can then compute perturbed image by calling evaluate and then visualize side by side. Here we can see that most of the parts of the train and background are dropped, ablated, except the suit on the person running to catch the train. This shows that after ablating train context and the background in the image, the classifier starts focusing more on the human suit on the image. Now let's look how we can compare different input perturbation techniques and adversarial attacks side by side. To do so, we need to import Captum attack comparator, create an instance of it by passing our model and a list of comparison metrics such as accuracy or log it. As next, we define a list of input perturbation techniques such as image rotation, Gaussian blur, or any type of adversarial attacks such as FGSM, or we could choose PGD or other attacks that we are familiar with. We then call evaluate by passing our input image and the ground truth label. Evaluate returns statistics about the accuracy and the logits of the model, which in this case is visualized in a spreadsheet. As we can see from the spreadsheet, the random rotation and FGSM drop model accuracy from 100% to 19% and 0% accordingly, while Gaussian blur transformation left the model prediction unchanged. Now let's look into another area of Captum library called concept-based model interpretability. Concept-based model interpretability aims to explain model predictions in terms of abstract predefined concepts. Here we have examples of such concepts. For images, stripes and random images, and for text, it could be, let's say, positive adjectives and neutral terms. We would like to understand how important are those concepts for model prediction. In this case, we have sentiment analysis classification model that has two convolutional layers, conv1 and conv2, and we would like to know whether positive adjectives contribute to model prediction when making predictions using movie rating dataset, as also visualized on this slide. There is a well-known method called testing with concept activation vectors, TCAV, which helps us to quantify concept sensitivity to model predictions with respect to a specific layer in our model. In this case, we will consider convolution layer 1 and layer 2. In order to use TCAV from Captum library, we need to define the concepts first. In this case, we define them using concept class, which requires user predefined data loaders, which will help us to load concept examples batchwise. The goal of TCAV is to learn a hyperplane that separates concepts from each other. In this case, we'll learn a classifier that separates positive adjectives class from neutral terms class for any given layer L. The vector that is orthogonal to the separation hyperplane and points towards a specific concept class is called the concept activation vector, or CAV of that concept. In this case, we visualize CAV vector for positive adjectives. We can then take any text example, in this case movie rating review, as inputs and measure model sensitivity to our positive adjectives concept when making prediction for the inputs. To do so, we would need to compute the attribution of our input prediction with respect to selected layer L, for which we already computed the CAVs. And then we will compute the dot products between the attribution and CAV vectors. This gives us an important score of concepts when making predictions on inputs for a given layer L. This arithmetic operation happens under the hood in Captum when we use TCAV class by passing the model, in this case it's our sentiment analysis model, and a list of layers for which we would like to compute the TCAV score. When we call interpret on the instance of a TCAV class by passing inputs and a list of concepts, it computes TCAV score for each layer specified in the arguments of a TCAV class for all concepts in the interpret method. We can then visualize the TCAV score using a bar chart for each layer. In this case, we visualize TCAV scores for both convolutional layer 1 and layer 2 for both neutral and positive adjectives concepts. We can see that the importance of positive adjectives is close to 1, and for neutral concepts, it's close to 0. This is what we expect because we use positive movie rating samples to make predictions. We plan to expand Captum beyond the areas that I mentioned and add support for influential instances, model comparison, and similarity metrics. So to recap, I started talking about the attribution methods and how we expanded Captum beyond those methods, adding support for concept-based model interpretability and robustness metrics, attacks, and input perturbations that can help us to generate counterfactuals. We would like to invite you to try out our library and provide your feedback in forums or GitHub. And we are excited to explore new directions with respect to influential instances and model comparison and similarity metrics. Thank you.